Okay, so one problem that I thought was interesting that when I was younger I didn't know how to answer in the most rigorous way was the question of the shortest distance between 2 points, or the what kind of line is the shortest line between 2 points. So let me just write this here. Why are we not writing? There we go. Shortest distance between 2 points. Okay. So what exactly do I mean by that? Well, for example, if I were to consider 2 points, I call this x, I'll call this y, and I'll call this point A maybe, and then I'll call this point B. Well, you can draw all kinds of lines between these 2 points. Of course, we know the answer, that the shortest distance between these 2 points is a straight line. But let's see how we can prove that or demonstrate that. So it could be, any shape. Including, of course, a straight line. So how do we figure out what that distance is? And let me show you how to do that. Now we know that that this is going to end up being a straight line, and this is kind of a curvy looking line, but let me show you how we're going to do it. We're going to consider a little delta x, and of course the delta y that comes along with it. And if I think of this little line segment, which could be curved, for example, so we're going to call the length of it s, because that's the the standard way to denote that. But we'll assume that if we choose a small enough delta x, that we should be able to get a relatively straight line segment. And so any little piece that we get here in delta x, right, will roughly be a straight line. And so we can use the Pythagorean theorem, which says that delta x squared plus delta y squared is equal to some delta s squared. And so once we have this little delta s squared, we can basically integrate it from a to b. So what's that going to look like? That's going to tell us that s will be equal to the integral from a to b of the square root of, I'm just going to call it x squared, or well, we'll call it dx squared. I keep forgetting that I can use calculus. I'm already written an integral sign, so I guess that should clear that up, right? Square root of dx squared plus dy squared. So here I've just turned my delta x's and delta y's into dx's and dy's. And so the trick here is we want to divide out dx squared so that we can rewrite this. Oh, that's messy. A to b, and I'll write this as, I'm going to factor out a dx squared. So I'll write the square root of 1 plus dy over dx, quantity squared, times dx squared. And then we can just integrate from the x component of a to the x component of b. It's important to note that I'm going to call y dot is going to be equal to dy over dx. So that's the rate of change of y with respect to x. I know usually you use the dot for time derivatives, but we're going to use it here. And we're going to think of this term here as basically a Lagrangian. And what we're going to do next is we're going to use variational calculus to find the curve that minimizes the distance between these 2 points. So to solve that, there's a couple of ways, but the easiest way is just to use the Euler-Lagrange equations. And if you're not familiar with those, maybe at some point in the future I'll make a video that talks about Euler-Lagrange equations. But let's see, let me just write them down for you. Remind you that the Euler-Lagrange equations, Euler-Lagrange, say that the derivative with respect to x of the partial of L with respect to y dot, that's why I use the y dot, is equal to the partial of L with respect to y. And if we think about it, right, this derivative inside the parentheses here, since our equation L does not have a dependence on y dot, that's going to be equal to 0. So we can write that dl over dy. Oh, I'm sorry, not dy dot. The dependence on y. It has a dependence on y dot. It doesn't have a dependence on dy, though. So dl dy, whoa, where did it go? Come back. Which is equal to the partial with respect to y of this square root of 1 plus, I'm just going to write it as y dot squared, is equal to 0. And so that's going to be handy. So therefore, the derivative with respect to x of dl dy dot is equal to 0. So when is that true? Well, it's true when dl dy dot is a constant. So with respect to x anyways. So let's write that down. dl dy dot, this is the thing that's constant with respect to x, but it's not constant with respect to y dot. So we need to take that derivative, and that's going to be equal to, well, the square root gives us a factor of 1/2. Then we'll have the term repeated again, 1 over 1 plus y dot squared times 2 times y. The 2's are going to cancel, and so we just end up with, oh, I'm sorry, not 2y, 2y dot. 2y dot, there we go. We're just going to end up with y dot over 1 plus y dot squared. And that is going to be equal to a constant c. So now all we have to do is a little bit of algebra. I'm just going to square y dot to get rid of that square root. I think you can see where this is going now. Now I have two terms with y dot in it, and so we're going to end up getting y dot squared times 1 minus c squared is equal to c squared. That's the c squared times 1. This, of course, means that y dot squared is equal to c squared over 1 minus c squared, which means that y dot is equal to c over the square root of 1 minus c squared. And now I'm going to rewrite this as dy dx is equal to c over 1 minus c squared. And that's pretty much it. So what does that tell us? That tells us that the slope of this curve, whatever it is has a constant slope. And what has a constant slope? Well, a line has a constant slope. And that is basically how you demonstrate, using variational calculus with the aid of the Euler-Lagrange equation, why it is that the distance between 2 points is a line. Now this can be more broadly applied. Let me just turn the recorder on the iPad off here. That can be, the same technique can be used for other problems. For example, one that you might try is the famous brachistochrone problem that was proposed by, I think, one of the Bernoulli brothers. Maybe I'll do a video on that later. That's a neat problem. I'm not sure I've ever solved it myself, but it's probably doable, especially with modern techniques like the Euler-Lagrange equation. But when you move forward in physics, especially when you get to the upper level physics courses, right, you're going to use this Euler-Lagrange and basically principle of least action quite a bit. And so this formalism turns out to be very useful. And so I just want to make a quick video demonstrating something that, for me, eluded me for a long time when I was young. You don't see it in a lot of places. I remember one time I bought a book because it touched on this subject matter, and I got the book and it just stated the problem and stated the solution, but didn't provide any guidance as to how to actually do it. And it was a thick book. It was one of these Dover classic books, and I didn't have the patience to read the whole thing, and maybe if I did, I would have been able to do it back then. But anyhow, just a little short video on something I always thought was kind of neat. And I hope you enjoy it.